number 10 is saying that the probability of being a boy is 0.55, right?
Probably, yeah.
So do we use the 0.55 or should we do the other method?
Yeah. You should look at girls then because it's gone past 50%, yeah.
I don't understand what will be is right because probability of seeing at most 5 such pins in a sample of 30. So I need 30.
Yeah.
And we need 5 or less because at most they want 5 such pins.
And what did you get for P?
Probability estimate is 0.35.
Yeah.
Yeah, so 5 or less, 0.35. The answer is 0.0.
Yeah,
2, 3,
yeah.
It's wrong.
Yeah, that's what we said. That's the answer. I think I'll do 10, 11, 12 in the tutorial then.
Yeah, please.
Yeah. Because I think the answer's wrong there. But 1 to 9 was okay?
Yeah.
Yes.
Okay, we'll continue. Okay, continue. Yep. So far our random variables have been, are we listening, guys? Could someone wake up in the bar? What? Wakey wakey. Right. So far, our probabilities have been discrete. What I mean by that is the binomial, you could have 5, 6, 7 successes. If you roll a die, you could get a 1, 2, 3, 4, 5, or 6. Okay. So here's an example. You have x, and the probabilities, let's just make it 4 possibilities. Let's say x could have been -1, 0, 1, 2. And let's say that's 0.3, 0.2, 0.1, we'll say, and 0.4. Now, it's true most things we measure are discrete. But sometimes we're measuring something or looking at something which is continuous. So what I mean by continuous is something like a person's height. A person's height could be any value. It could be, for example, 125 centimeters, or it could be 125.2. It's not from a certain number of possibilities. It could be any height. Okay. Compare this to say something like shoe size. Shoe size could be 6, 6.5, 7, and so on. You never get a shoe which is 7 and 1/8. Okay? So this is the difference between discrete and continuous. And everything we've been looking at so far has been discrete, that you could only have certain values. But we want to change it now. We want to look at if you have continuous. So I'll just remind you of a histogram. Let's say 0, 1, 2. And in this histogram, I'm using the area to represent the percentage. So, for example, this area is, let's say, 0.5, 0.3, and 0.2. So that means 50% of the time I get a 0. 30% of the time I get a 1. And 20% of the time I get a 2. But I could have subdivided more. Instead of going 0 to 1, I could have gone 0 to 0.5 and then to 1 and then to 1.5. You know, so I could make more boxes. And if we continue this process to make an infinite number of bars, we might get something that looks like this. It looks smooth, but it's actually not really. What's happened is we've just made the bars so thin that it just makes a shape that looks like it's smooth. But the meaning of the bar, it's still the same. So for example, if there's 0 and there's 1, and if I was to calculate this area here, what would I be calculating? Area under the curve. And what would it represent? Yeah, but I mean for the story. Like for example, imagine that this came out to be 0.2.
All possible.
Yeah?
Converging to 0.2.
Yeah, but what's 0.2? It means 20% of the time I get between 0 and 1. I get somewhere between 0 to 1. Yeah? So in other words, here the area equals the probability. But that's the same as what's before. It's just this time, instead of being stuck picking only certain values, you're actually completely free to pick any value. So if I said, what's the chance I'll get a number between 1 and 1.2? Well, there's 1. There's 1.2. And if I calculate this area, then I have the chances of getting between 1 and 1.2. Are we getting the idea with this? So, the shape of the curve depends on the problem. But there's a particular special one which we'll look at today, which is called the standard normal. So this is how it looks. If you want to try and roughly draw this. The chance of getting a 0, and we usually call it Z instead of X. The chance of getting a 0, something near 0 is quite high, and then it decreases quite quickly, like this. So most of the shape is between -2 and 2. But technically speaking, it goes all the way out to minus and plus infinity. And you can use this to answer questions. So if I said to you, what's the probability? What's the probability that your Z will be between, let's say, 1.1 and 1.2? You would have to go to your graph, mark off 1.1, mark off 1.2, and the chance of getting something between 1.1 and 1.2 would be this area here, as an example. That is the probability of getting between 1.1 and 1.2. But some things are kind of obvious here. This graph is symmetric, so maybe someone can tell me, what's the probability that your Z will be less than or equal to 0?
Second 4 minus.
Oh yeah, but it's a number. 50%. Because remember, what should the total area be? 1. So the probability that Z is between minus infinity and infinity is 1. Obviously, Z has to be somewhere between those two numbers. So the total area is 1 here. Now what I'm going to do now is I'm going to show you how to calculate these probabilities. But just to help a little bit here, if you just look at the first question, can you see the first question in the book there? Oh, also before I do that, just so you know, a short notation for writing standard normal is to write N01. That means standard normal. We'll explain the meaning of that in the next class. If you look at question 1, what I've done, are you all looking at number 1 there? I've used a computer program to generate 10 examples of Z. Look at those 10 values of Z. Which is the biggest one?
0.
1.87. Now that makes sense because if you look at my graph, I said most of the values are between -2 and 2. So I don't expect values outside of this. Okay. How many of those values, let's see, how many of those values are less than 0? Are you sure? 5. And how many values do I have? 10. So what's the probability I'm less than 0? 50, which is exactly what we just said a moment ago there. Okay. What about if I said, now, I don't know if we can do it. What's the probability of being between 1.1 and 1.2? So how many numbers are between 1.1 and 1.2? Do I have any in that example? No. Yeah, so I with only 10 numbers, I can't see what that is. It's too small then. Okay. So, anyways, let's go on to the calculation here. So this graph has an exact shape. There's actually a formula for it. And the formula for the shape of this graph for calculating the probabilities of z is 1 over root 2 pi e minus a half x squared. So for example, let's say I want the probability of being between 1.1 and 1.2. Probability that z is between 1.1 and 1.2. How would I calculate this area?
Sub the x.
Yeah, well, what's the technique in maths for calculating area? Yeah, so what would this be then as a problem? Integrate 1.1 to 1, 2, yeah. Integrate this. Yeah. Now, here to integrate this, no, you can't. It's not actually possible to integrate this. But that's okay, because you can do this on a computer and they've put all the answers in the table book, just like with the last lesson. So if you go to page is it 9? Yeah, 9.
What are the coefficients of x?
The coefficients of x. 1
The
over root 2 pi. Okay, can I continue? So the problem here is you can't integrate. It's actually not possible. So we need to use the formula book. So let me show you how to use the formula book here. The way the formula book works is like this. You can look up a value of z in the formula book and it will tell you the area to the left. So, for example, if you want to know the area between these two, what you could do is look up the value of 1.2. Yeah, and then look up the value of 1.1 and then subtract the two answers. And that would give you the piece you're looking for. Now, there's a symbol here that means to look it up in the table book. So if I write this symbol here, that means you look up the value of 1.2 in the table book. So if you go to the table book, you look down the side, you see 1.2? What's the value to the right of that?
0.8849.
0.8849. Now before you ask, if you're wondering what the extra values are for,
These are variances.
no, the extra values are for an extra decimal place. So if you want 1.21, that's the value across to the right. So what would be 1.21? 0.8869. And 1.22? 8888. Okay. All right, what's the table book value of 1.1, please? 8643. Right, if I minus these, I get my answer. So what's the difference here is about 2%. Isn't it 0.02 roughly? 0.0206, is it? Yeah, so about 2%. Yep.
Yeah, so do we have to show that? Because you can just solve it using the calculator.
You're not in the exam, you can just check the answer.
So why can't you integrate?
There's no maths function which would be the answer. There does not exist a maths function which is the integration of that. No, but that's a numerical approximation. It's not exact.
It gives us an answer.
Yeah, to 4 decimal places, but technically it's not exact. Do you know what I'm saying? It's only an approximation, but it's accurate to like 6 decimal places.
Does it give a really long answer?
Yeah, but my point is it's not exact. It's only approximate.
So we can't use
You can use the calculator to check your answer, but in the exam they want you to use the formula book.
What did you say? Is when you move across
An extra decimal place. Let me give you one to try. What is the probability that Z will be between 1 and let's say 1.51? Yeah? So what do you look up first?
1.51.
You look up the 1.51 and then minus, and you look up 1. And when you minus those two answers, what did you get?
0.09.
Well, tell me what the first one was. 1.51. What was that?
0.9345.
Minus 0.8413. Okay, so what's that, about 9%, is it?
0.0932.
Okay, so that's rough, well, exactly 9.32%. So that means 9% of the time this special variable called Z will be between 1 and 1.51. Now, I know it seems a bit unusual that we're studying this random variable Z so much, since I've not actually said what this Z represents. But in the next lesson, we'll connect it to things in real life. Right now, we're just imagining Z as some special random variable that is usually between -2 and 2. Okay? Right, let me give you a harder one now. I want the probability that Z is more than or equal to 2. More than or equal to 2.
So 1 minus.
Yeah.
minus less than
It should be a pretty small number, like, a couple of percent.
0.0228.
So, I think a lot of you figured out the answer would be 1 minus, and then you have to look up 2, because 2 is this area. And what did you say this was? 0.0228.
228.
Okay, now, probability that Z is less than or equal to -1.
You add 1.
Now you see, we've got a small problem here, because if you look at your table book, what's the smallest Z value? 0. But let me show you the trick here. If I go to the side, Yeah, symmetry, yeah. Imagine you want to look up minus z, which is here. Okay. Well, that would be, hang on. Hold on. There's z here on the right. That would be the same as the probability of being more than this z.
So 1 minus probability of z.
Yeah, so that's 1 minus z. So in other words, if you want to look up a minus, you just do 1 minus and you look up the positive. This is a very useful rule here. Yeah. So, yeah, this is equal to table book of -1. But you can't look up -1, can you? So this is equal to 1 minus, and then you look up the value of 1.
.8413.
8413. So that's about 15-16%, isn't it?
Yeah, 1587.
So about 15.9% then. So, again, how likely is z to be less than -1? About 15.9%. So, if you have 10 of these z numbers, how many would you expect to be less than -1? Roughly. 1 or 2. 1 or 2.
1.5.
Yeah, so 1 or 2. Now look at those 10 z numbers I made for you. How many of them are actually less than -1? Yeah, less than -1. Just one of them. Which one? -1.44. That's that's what I was saying, about 15%. So if you have 10 numbers, that means about 1 or 2 of them. Yeah? Okay. Okay, just 2 more small things to note. There isn't really much of a difference. Come on, you two. If I said z less than or equal to 1, or if I just said z less than 1, they're actually really the same thing. Because less than or equal to 1 means you could have 1.0000 or less. Here, less than 1, that's 0.9999, etc., or less. Really, especially when you round it off to 4 significant figures, there isn't any difference between the two. There's still technically no. Technically no. But I'm trying to give you a simple reason why it's not different. Technically this is correct, equals here. And the reason for that is the next thing I'm going to show you. Can I scroll down? Right. So we're back to our z. By the way, just to give you a little bit of vocabulary, this z, we call this, remember I said the standard normal. You can also call it N01, and sometimes people call it a z score. It's just a bit of vocabulary for you. Anything else? No, I think that's the main one. Yeah. No, like I'm just saying, I say z, but some people say z score. Just if you hear someone say that, it's the same thing. Okay. Right. What's the probability that z equals 1? I'll let you try and calculate that. Now, I didn't say less than 1. I said equals 1. Now visualize it. So I'm at exactly 1, and I want exactly 1, so it means I want this area.
But it's not a range.
Exactly. The area will be the base by the height. There is no base. The base is how wide? 0.
So 0.
This is important. This was in the exam, I think, last year for like 1 mark. They said, what's the probability that z equals 1? Or what's the probability that z equals 2? All these. It's always 0.
That doesn't make sense.
Doesn't it? Or does it?
I don't see how this will be.
Because you can get one.
Can you? Let me give you, I was going to do an example here which will explain.
You can get one.
I'm going to do an example that will explain.
How's the base?
Trust me. The base is 0 because there's no thickness to it. You're just at the point 1. There's no thickness. Yeah? Amjad, you look so worried. Just look at the next example, okay? Look at the next example. So, come on. So for our next example, okay, we were talking a lot about z. Z is a special number. It's somewhere between -2 and 2 usually, okay? There is another random variable which is quite important called u. And u is between 0 and 1. And it's anywhere between 0 and 1. So for example, each value is equally likely. So the graph looks like this. There's 0, there's 1. You can't be less than 0, but you could be equally anywhere between 0 and 1. So for example, the probability that u is between 0 and 1 equals 1. The probability that u is between 0 and a quarter is 0.25. The word u stands for uniform. Yeah?
Wait.
Huh?
It's 1. It's not 0.25.
What?
Because it's always you.
Oh no, you're getting very confused now. Oh no, just keep listening. Anyways, the way you make u is like this. This is how you make u. So what you do, you start off with 0 point. Now please pay close attention. Etc. Each digit is picked equally likely between 0 and 9. So here you could get a 0, a 1, a 2, a 3, a 4, etc., etc. Okay? So here's a random u. 0.2694, etc., etc., etc. It can be any number because each digit is picked equally likely. Okay? So my question is, what is the probability that u equals a half? So if you want to get a half, what will you need the first digit to be? 5. What's the chance of getting a 5 here? 1 over 10, because you can count 0. Right, what will the next digit need to be if you want to get a half?
0.
What's the chance of getting a 0? What will the next one have to be? It'll have to be 1 over 10. What will the next one be? Now this continues forever. So this is 1 over 10 power infinity. And what does that equal? 0. So it's impossible to get a half. This is the point. When you have something that can be any value, it's impossible for it to be one precise value. It can only be between two ranges. That was for 1 mark, by the way, on the exam.
So you don't know the chance of it being a value, but you know the chance of it being between.
Yeah, exactly. That's the key. You can never know the probability of getting a precise exact value. You can only ever know what's the chance it'll be between two values.
It could be infinite.
Now, I'll give you a simpler example.
What's the probability of getting 2?
0. Because it has to be between 0 and 1.
Yeah, it's that one.
Huh?
It's 2.
No.
What?
Can't be 2.
It's 2. 2691.
Oh, what? No, you're very confused, Amjad. I'll tell you the best thing you can do is sit quietly and just try to let it all in. There we go. Okay. Amjad, listen.
But wait.
I'm continuing now.
I keep thinking that's one.
No. Okay. Let's talk in more thinking. Right. I'll give you an example in real life. So suppose I ask you, I have a group of students. What's the probability that I pick a student and their height is between, say, 1.2 and 1.5 meters? Okay? No, it's not. Somebody's going to be between that height here, I think, okay? Yeah? Now, if I said, I pick a student, what's the chance that their height is exactly 1.2? And you say, well, somebody's height could be exactly 1.2, so it's not 0. But then you realise, oh, well, I said exactly 1.2. So maybe you measure someone and you think their height is 1.2, but then if you measure more closely, it could be like 1.2000001. And is their height exactly 1.2?
No, it's 0.
No.
What if there is someone's height 1 point?
No, it can't be. Can't be. It might look like that because of the measuring device. But remember, you can, if you could measure exactly, you might discover that they're not exactly 1.2. It's impossible to be exactly anything. You can only be between possibilities. Okay? Yes? What?
Infinite decimal cases.
Yeah, that's the key reason.
But that's exactly. It's a pin code. You can't have two.
I never said it was a pin code.
Oh, it's not pin code. What about if it was a pin code?
If it was a pin code, the answer is yes, you can be. But the difference, what's the difference between a pin code and this? A pin code is discrete. A pin code can only be certain values. But the things we're looking at today are continuous. They can be any value. Okay. It's okay? Yeah. Maybe your cap's on too tight today. I'm not sure. Okay. You should start from question 5. Question, yeah?
So there are things that are exactly a certain value. So there is, like, for example, there is this brick in France that's exactly 1 kilogram, which is
No, it's not.
It was used as a scale. What is 1 kilo? So
Okay.
that is 1 kilogram exactly.
You could define it as 1 kilogram, but
It defines what 1 kilogram.
it defines it is. But the problem with this is the moment you make any type of measurement. So, for example, that brick is exactly 1 kilogram.
Yeah.
So maybe I measure this. I can never know if it's exactly 1 kilogram. Because whatever I measure it, I can't get it exactly to 1 kilogram. Now you could say, but the brick is 1 kilogram. But you're not measuring the brick. You're defining it to be 1 kilogram. Whatever it is. Do you get what I'm saying? So it's like, if I, for example, if I define pi to be 3.1415, etc., etc., etc.
I know not this. Maybe it's easier.
Pi is exact. But the moment I try to write it down, measure it, I can't be exact because I have to stop my decimal point somewhere. It's the same with the measuring. If I measure its mass, I have to stop at some point of accuracy, which means I can never know if it's exactly 1 kilogram. It's theoretically possible, but you can never know that. That brick that's 1 kilogram, by the way,
They stopped using it.
yeah, I don't think it's 1 kilogram anymore because some of it has decayed. So I'm not sure.
That's why they went all digital now.
That's why they're trying to move digital, yeah. But as long as something is continuous, it's impossible for it to be exact. If it's discrete, you can have it exact.
They actually changed it this year.
Huh?
They actually changed it this year.
Has it changed?
Yeah.
So what's the definition now?
I'm not sure.
I'll have to look it up.
I read the news that they...
Oh, I'll look it up. Okie dokie.
Sir, in the answer, number 5 and 6,
It's wrong.
yeah.
Wrong way around.
Slightly, it's slightly.
Oh, it's the same number.
Yeah, but it's 0.8869, but it it's 8868.
Yeah, but there's 6
Oh, I
outputs,
used a computer program to be more accurate here, yeah.
which you can never be very exactly accurate.
No. Yes? This better not be about the pin code. What?
So the probability of getting
1 sec, he's asked me about something. Go on.
so the probability of getting any of these numbers is 0.
Correct.
Oh my god.
Now, young Kang, what were you saying?
And make a statement
Yeah.
if it doesn't exactly if it's true.
Yeah,
If the variance and
Yeah.
standard deviation
Yeah.
in normal distribution
yeah.